All right, so you should be able to see this. I'm sharing my screen. This is the assignment. It's called Other Non-Constant Rates or More Non-Constant Rates, which is the assignment name. It looks like this. I've already downloaded it and reopened it in Kami, and it looks like this. Okay, so we're going to talk about volunteer crew at a house for low-income housing. Completing one house takes 200 days of labor. How long does it take one person to complete one house? I don't know. There's not enough information here. You're absolutely right. So let's figure this out. We're going to go into here and we're going to figure out what they're talking about. So here we are. Dylan's part of a volunteer crew, blah, 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 blah. Well, hey, that's like exactly what it said in the question. Let's find out what they're talking about. So, well, there's a house. And there are two people. Okay, two people work for how many days to build this thing? It takes two people 100 days. Okay. Okay. So it takes two people 100 days. What if I move on? What if I have more people? 4 people. You could probably guess twice as many people, half as long. Now, just so you understand, this is not always how it works in real life either. This is assuming everything is proportional, and often in life things are not proportional. There comes a point at which, well, 8 people takes 25 days. That seems right, right? There comes a point at which more people doesn't really help too much, especially if you've got some issues with organization. But we can talk about that another time. It's still going. Wow, 20 people. Now we're going to fill out this table in a moment. In fact, I believe it's right there. All right, and we're going to make that. How long does it take one person to complete one house? Well, we decided it takes one person 200 days because one person, 200 days, 2 people, 100 days. That is just something that they want us to record. So we're just going to write that down. Okay, so we've done that. Now we're going to fill out this table. We're going to make a graph really fast. So to make the graph, I need to remember which one's X and which one's Y. Well, we're deciding based on how many people there are, how many days will it take? So the number of days depends on how many people are in the crew, right? If there are 40 people in the crew, it'll only take 5 days to build it. We're basically making this graph, just for the record. So I might as well just use the same number, 10, 20, 30, 40, 20, 40, 60, yeah. Okay, so we're gonna fill this out the same exact way because why fight it? Am I right, guys? Am I right? So this right here is the 10 days, no, 10 people. Now, you know what? Yeah, we'll do it the way they said. Sure. You could count by a different amount. If you take a look at the numbers there, you count it up by, let's see, right now we're counting up by 5 each square. Each 2 squares is 10. Now what I would do actually, I would count by 4s. So 4, 8, 12, 16, 20, 20, and so on and so forth. And we would get to 40 a little bit later. Almost all of these numbers would work out well with it. So just a thought. But this is fun. And then this was also 10 actually. 10, 20, 30. No, we didn't do that. We did 20, 40, 60, 80, 100. 100. Let's see if we can make it work this way. 100. Oops. All right. There's 100, 80. So all of this work is just make sure that we can fit all of the numbers on in a nice, comfortable way. There's that one. There's that one. There's that one. There's that one. And there's that one. There. Now we have a graph set up. Now we notice that if it takes 2 people to go 100 days, let's go with black for this chunk. We'll make these bigger so they fit. 100, 2 days. Well, this is 5, 4, 3, 2. 2 is going to be about there. Boom. And in 4 days, well, with 4 people, it takes 50 days. 4 is going to be right here. 50 days is going to be right here. All right. With 8 people, it takes 25 days. 8 is going to be close to 10. 25 is about here. Okay. 10 people takes 20 days. 10 people takes 20 days. Well, that's easy. 20 people takes 10 days. 20 people takes 10 days. And 40 people takes 5 days. 40 people takes 5 days. Notice, this does not make a straight line. It doesn't make a straight line like this. Instead, it makes this curve. Cool, huh? This is called a hyperbolic curve. Hyperbolic. Or a hyperbola. That shape of curve is called a hyperbola. This is also from, we're going to talk about this in a moment, from inverse variation. We just did an assignment, well, not anymore because Christmas came and went, but we did, oh, is it increasing or decreasing? I'll give you 5, 4, 3, 2, 1. Notice it starts up high, it goes down low. Now it slows down as it's going down low, but it never stops going down by smaller amounts, but it's always going down. So yes, it is always increasing. Oh, actually not yes. It is. And I want that to be purple. That way I can see what I wrote. You can see what I wrote easier. Boom. Okay. When the product of 2 quantities remains constant, what type of function models that relationship? Let's see what that looks like. So we're going to move on. We're going to look at these things. I know the answer, but we might as well. Look at that. There's our graph again. Now, this is called inverse variation. Notice that's what they're saying. So this graph shows a decreasing function. Yes, it does. We just talked about that. Notice that the product of the 2 quantities remains constant. What are they saying by that? Well, product means multiply. And our 2 quantities, well, those must be our 2 numbers. Let's see, what's 2 times 100? 200. What's 4 times 50? 200. What's 8 times 25? 200. 10 times 20? 200. 20 times 10? 200. 40 times 5? You guessed it, 200. All of these multiply to make 200. That's the pattern here. Now, this is similar to something we did. This is called inverse variation. Now, we learned direct variation in the past. So, inverse variation, I might as well when x times y equals something. What we learned in the past was direct variation. Now, if you remember, direct variation was basically point slope form. It was like a line with a slope. It was not this shape. It was not curved. It was a straight line. Direct variation, which was y equals k times x. You can go back to an old assignment to see that. This is direct variation. Inverse variation is what we're talking about here. They make a completely different shape. And what's important is you notice this is a non-constant rate. How do we know? Well, because constant rates are always a straight line. Constant rates go like this, or like that, or like this, or like that. They're always straight. Non-constant rates can change steepness. They have lines that curve. This line right here if I turned this into a line, it is definitely a line that curves. So it's a non-constant rate. That's what we're talking about here. Okay, so that's one type of non-constant rate. We're going to look at other ones. Okay, so this one's called direct inverse variation. It is very useful to know about. You don't really touch it again until pre-calculus, maybe algebra 2, probably algebra 2. Take another look at the table and graph in the volunteer situation. Okay, is the rate of change for this constant? Oh, we just talked about that, didn't we? Remind me, is it 5? Pause if you need to think about it, or type it in yourself and see if you get the same answer as me. All right, now I'm going to talk. Okay, so is it constant? Oops. No. No. The rate of change is not constant. We can tell because the graph is not in a straight line. Well, not form a straight line. That's better English. Not form a straight. Why did I do form? I want does not form a straight line. You may not like that I do caps. It seems like I'm yelling while I teach, but I just want to make sure if anyone ever reads this, they know that I'm talking about a negative and not a positive, because I don't want to communicate the opposite of what I mean. So if you ever wonder why I do capitalize no's and nots, it's so that if anyone's reading it really fast, they go, oh, he means definitely that it's a negative statement. How can you tell from the table? Well, looking at the table, what do I notice? Well, this guy changes by 2 and that guy changes by 50. So if this guy changes by 4, that should change by twice as much, right? But it doesn't. So if I find out the slope, like 2, a change of 2 in the crew size should change the number of days by 50. And so then I continue to try to expect that. It changes every time. So if I make a fraction of y, what does that mean? If I take 250, so if the slope's staying the same, then 2 divided by 50 should be the same as 4 divided by 25. Is it? Or actually, I did that backwards. 50 divided by 2 should equal 25 divided by 4. And that would mean it was having a constant rate. The problem is that doesn't make the same fraction. 50 divided by 2 is not 25 divided by 4. So I know that the slope is changing because I just found the slope twice. That's how you find the slope. So that's what's going on. All right. Monica's going to measure the distance of a balloon from the top of Mount Franklin as well as its height in general. Okay, let's do that. Okay, so distance in kilometers from the mountain. She's getting further and further away from the mountain. She's also getting higher and higher. Okay, so we're going to graph that up here. Let's do that real fast. 8 meters in height. Which one's this one's 8 meters in height? Okay. And then this is distance from the mountain. So 10 is going to be about here, just past 8. And 8 is going to be almost not even off the ground. Like, we'll go with that. That looks about right. Now I'm guessing with these amounts, and that's okay. Okay, now it's 32 feet in the air, closer to 50. At 20, 20 is going to be a little bit past 16. It's actually going to be between 16 and 24. And it's 32, which is about there, we'll say. Okay. Okay, now 72 feet in the air, that's going to be about halfway between these. But 30 is going to be just under 32. Around there. Okay, so we did this, we did that, we did that. Oops. Now we're going to do 40. 40 is right here. Oh, yeah, it even has its own number. That's nice. And 128. 128 is pretty close to 125, which is halfway between 100 and 150. So it's just a little bit more than half. There, that's close enough. 50 is going to be a little bit more than 48. And I got to go all the way up to 200. All right, 60 is going to be 288. 60, 275 is going to be in the middle. 288 is going to be a little bit higher, like there or something. All right, and 70. 70 right here, just under 72. And 392 is just under 400. There. That's about right. Now notice this curve, and I do call it a curve, it's getting steeper as we go, isn't it? It's not exactly the same shape as the last one. It's a different type of thing. Is it constant? I'm going to give you 5 seconds to think about it. And the answer is no. The graph forms a curved line, not straight. Remember, constant rates always make a straight line. Okay, we're going to find the differences in the balloon's heights. Now, this is a cool way you can try to figure things out. Later, we do this a lot to actually find things out, or to find what we call the degree of a function. Okay, so what we're going to do is we're going to use our math skills, and we're going to figure out how much things change by. This is called the first difference. So if I subtracted these like so, what number do I get every time? Hopefully you're seeing it. 10, 10, 10, 10, 10, and 10. They're always going up by 10. Now the bottom one is not always going up by the same amount. This is one way we can always tell it's not linear. If things are linear, then these numbers, if these are all the same, then the bottom ones should all be the same. Let's see if they are. This time I'm not going to put the little doodlies. I'm just going to type the numbers in. So from 8 to 32, that is up 24. From 32 to 72, that's 40. From 72 to 128, that's 28 plus 28, 56. From 128 to 200 is 72. From 200 to 288 is 88. From 288 to 392, that's 104, I believe. All right. We got those. That's great. what do I notice about this? Well, these stay the same. Even though the distance from the mountain in meters, kilometers is going up steadily by 10 feet. 10 kilometers, I guess. That is a long balloon ride. They're going a long ways. However, this right here is not going up by the same amount. So what I can say is, since distance changes by the same amount, and balloon height, GHT changes by different amounts, this cannot be this is not changing a constant rate. Why? Because the slope is changing. The slope would be one of these divided by one of those. And that fraction is going to change every time. 10 and 56 are going to make a different fraction than 10 and 24, and so on and so forth. What pattern do you see looking at first differences? Just did that. Sometimes this really bugs me. It changes by more and more. Would you agree? So this guy always goes up by tens, but the bottom one goes up by more and more. That's what we just said. It's being very repetitive. Now we're going to ask about what's the second difference. Okay, and then we're going to find that. So the first difference is when I subtract once. So first difference, 10. 10. 10. That's what we just did. Why do we call it a difference? Well, difference means to subtract. And that's how we find these numbers. We're subtracting. 20 minus 10 is 10. I'm going to scoot up a little bit so I can see the numbers so I don't have to think anymore. Thinking is the worst, isn't it? Okay, 56. Oop, not 82. 72. 8. 104. Okay, we're back to here. So this is the first difference because I subtracted once to find each of these numbers. So 32 minus 8 makes 24. That's how I find out how far apart they are. That's why difference is called difference. If you subtract, you get a difference. That's called a difference. So this is the first time I subtracted. Now this is called the first difference. The second difference would be if I did the same thing. My answers. So from 24 to 40, for example. How far is it from 24 to 40? Well, that's 6 plus 10, that's 16. 40 to 60, 56, 16. From 56 to 72, 16. From 72 to 88, 16. 88 to 104, 16. What we notice is the numbers I just got from the first step are all 16 apart. I can do the same thing up here, but it's a very boring answer. Zero, because 10 minus 10 is 0. Well, it's not changing. So how much it changes by? 0. Okay. So if I want to find second differences of something that's constant, I get zeros. This doesn't make any sense. So, but if you got something where you figure out how much it's changing by, sometimes it pays to check again and see how much is the change changing by. And I can find out that's always changing by 16. Let's find the first difference. Oh. So that hopefully explains what we just did here. Once I find the first difference, I can subtract these numbers, the purple ones, to find the second difference, the red ones. And if I wanted to do that again, I could find the third difference and the fourth difference and the fifth difference. Although it's kind of pointless now. We got a pattern. We found a pattern, and that's what we're looking for. Notice this pattern, the second difference was always the same. We do that to check to see something. The ratio of the second differences in the balloon's height to the first questions. What do you notice? Well, so we're going to compare our second differences in height to the first differences of distance. Second difference is 16, and first difference is 10. 16 and 10, 16 and 10, 16 and 10. It's always the same. The numbers are 10 and 16. They do not change. So, if we make a ratio of them, a fraction, so I know that I'm going to get, go back to purple. Red is just a little too angry looking, isn't it? That's how I feel, at least. Okay, so we notice that 10 and 16 will always make the same fraction. And so that's good to know. Okay, what type of function models data like these? In what ratio of second differences of the first difference is constant? Okay, blah, 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 blah. In which the ratio of second differences and first differences is constant. They're saying a lot. But what we're noticing is, if I subtract twice, I get a pattern instead of numbers that are changing by different amounts. Okay, so these ones, when I subtracted them, the originals, I got these numbers, 24, 40, 56. I don't see a pattern there. Maybe I'll subtract again. Oh my gosh, there's a pattern the second time. That's something we look for. That's called a second degree function. So you know second degree function is when I have x with a 2. That's what makes something second degree or quadratic. You can't have something bigger than that, but you have to have something with an x squared. You can have other numbers in front. So the official way to write it is y equals a x squared plus bx plus c. And A, B, and C are just numbers, but we'll get to that later. This is a really important one for high school. Quadratics are like the bread and butter of high school. We learn how to do the quadratic formula and all that fun stuff. It's going to be fun. I hope we get to it this year. Okay, now we're going to graph data created by folding paper to create rectangles. Okay, so I take a piece of paper. Let's find out what they're talking about. That's good to know. Let's see. We did this. We did that. We did that. Oh yeah, there's the hot air balloon. Here's the table. And look at that, first and second differences. We're just filling out what they said. And there's quadratic function. That's the one I just wrote out.
Y equals a squared plus b.
Yeah, whatever. And now we're moving on to folding a piece of paper. If I fold it in half down the middle, that means now we're going to find out the number of rectangles it makes. And then I unfold it, then it's got one on each side of the fold, right? But if I fold it once and then fold it the other way and fold it the other way, I like fold and then fold what's folded and fold what's folded, then I end up with 4, well, let's see, 8 rectangles formed right here, right? So you're just kind of folding to make rectangles in the paper. That's the name of the game. And here's what we notice. This is always going up by 1. And this one, it's going up by a different amount each time. That's kind of like what we had before. Maybe this is the same as the hot air balloon. Or maybe it's another type of function. Okay? So what do we notice about the rate of the data? Now you might notice right away the pattern of these numbers. Okay? This is this is not quadratic. This is what we call an exponential function. We're going to talk about what that means in a moment. But first, let's graph it. What do you notice about the rate of change? Okay, so let's graph it. Got this. Instead of 2, let's change it back to 4. We got to label this thing. All right. Okay, so we've got 1, 2, 3, 4, 5. That's easy. 1, 2, 3, 4. So I'll put that back up here so you can see it better. Oh, up there. Great. The 2's a little bit too early. 3, 4, and 5 are great. Okay, there we are. We got 1, 2, 3, 4, 5 for our number of folds. Now we're going to do our number of rectangles. Right. And let's see, that's got to go up to 32, 10, 20, 40. That seems close enough, and I'm feeling lazy. So 10, 20, 30. The cool thing about these shapes, I mean, I'm just going to tell you up front, we're not going to actually prove it because that's something that you would do in college, but these shapes that we're finding, this shape, oh, did we graph the hot air balloon? There it is. And this shape, the hyperbola, and the one we're about to do, they are constants. You will see these shapes for the rest of your life in math, and they never change. As long as this is a consistent scale, and that's a consistent scale. Like they don't count up by different amounts every once in a while, which would just be a bad graph. As long as they're a consistent scale, the shape will always be the same. It might look a little steeper, a little shallower, like we were able to do by changing scale, but the shape itself never changes. So that's kind of cool. 0, 1. Boom, about there. Okay, when you have 1 fold, there are 2. 1 fold, there are 2. Okay, when you have 2 folds, there are 4. Two folds, there are 4. 3 folds, there are 8. 3 folds, there are 8. 4 folds, there are 16. 4 folds, there are 16. 5 folds, there are 32. 5 folds, there are 32. Now this looks kind of like the last one. It curves and gets taller. But what do we notice is different? Looking at this curve, Where does this one grow by the most? Well, it grows up, it gets steeper like this. But if you notice, it's getting straighter looking as it goes up. It's looking more and more like a straight line the further up it goes. Whereas this one here, the further it goes, the less it looks like a straight line. It looks more like a straight line on the left side. So there are differences about these curves. They're not the same exact graph. Okay, they are a different shape, technically speaking. However, there are other ways to take a look at this. We're going to find the first and second differences. Okay, you very well may notice this always goes up by the same amount. Okay, this is called exponential. Okay, and one thing you might notice is it grows by the same factor. Okay, so what does that look like in a function? That's a function where we have y equals some factor like 2 to the x. And x is an exponent. It's not a number down below. It's actually the power that you're taking a number to. That's why this is called an exponential function. Okay? And exponential functions, you can find them because they always go up by a certain factor. Now, if we're talking about COVID, the factor, like the doubling time, like they were talking about doubling every 3 days, that's 100% one of these functions. You can model it using an exponential function, but usually the factor in real life is something like 1.035 or something like that, which means it grows by 3.5% every something number of days or something. Usually we don't have a factor like this in real life, like 2, because that grows really fast. Okay. So let's find out our patterns. This goes up by 1, 1, 1, 1, 1. There. It grows up by 1 every time. It's pretty straightforward, I think. I hope that doesn't baffle anyone's minds. All I did was, well, I didn't actually have to subtract because I can count. It goes up by 1 every time. But if you subtract the smaller one from the bigger one, you get 1 every time. Over here, we've got, this goes up by 1, but then it goes up by 2. And then it goes up by 4. Oops, not 3, 4. And then it goes up by 8. 8 to 16 is 8. And then from 16 to 32, that's 16. And here's where you notice a pattern. Where do those numbers look familiar from? Hey, those are the same numbers, like this. They're the same numbers. The crazy thing is if I do this again, this 1 to 2 is 1. From 2 to 4 is 2. From 4 to 8 is 4. And from 8 to 16 is 8. Now, eventually I run out of numbers to subtract, but you can do this forever. And it will always have the same numbers. Because, well, I mean, once you start the pattern, it's just going to continue. That's the way numbers tend to work. So that's kind of cool. So you can do as many differences as you want, and you'll never get closer to an answer. It'll always just repeat. That is a way you can tell that something is exponential. But then again, another way is if I can just notice that it grows times 2 every time, that's exponential too. So if you can notice something grows by the same factor, so instead of adding, we're multiplying, that's another way you can always do it. Okay, we're going to take a look at these. We're going to figure out if they're linear, quadratic, exponential, inverse. Okay, so inverse was the first one we did. That means that x times y makes some number. Okay. whereas this is some number to the x power, and this is x to the second power. And this has an x and a y. It's a regular x and a y. You can have other numbers with them. There. All right. So we got that. These are not the only ways to write them. There are lots of ways to write the first three. The last one is the only way to write it. So we're going to take a look at this guy. 1, 2, 3, 4. This is going by ones, right? I'm going to pen a little bit better. Oh, okay, so this grows up by ones. 1, 2, 3, 4. This one goes up by, from -3 to 0 is 3. From 0 to 5 is 5. From 5 to 12 is 7. Well, that didn't get me closer. But do you see a pattern? 3, 5, and 7, how far apart are those ones? Well, they're 2 and 2. Notice the second difference is the same. So this must be quadratic, because that's quadratic functions do. Okay, I'm going to erase the 2's just so that we can see the next assignment. But that's what we're doing. Okay, the next one. I'm going to give you a second to pause and try to figure out what the next one is. All right, I'm assuming that you just paused and did it and gave it your best shot. Always try to guess, okay? That's how your brain processes and thinks. So this one goes up by 1, 1, 1, 1. This goes up by 4, and 4, and 4. So this goes up by ones. This goes up by 4s. Correct? Consistently? Yeah. So if I make a fraction of them, I'm going to get, well, this goes up by 4, that goes up by 1. I'm going to get a slope of 4. Hey, that's linear. That's when the slope never changes. So hopefully you got linear. All right, next one. We've got 1, 2, 3, 4. That only goes up by ones. Very good. 1, 1, and 1. Over here we got this goes up by 2 and 4. No, it goes up by 4. Sorry. Can't count. 4 and 8 and 16. Notice these are the same number. Which one is that? Think about it. Okay, I'm assuming that you guessed that it is this one. Same number. It's exponential. Please finish the next 3, and I'm going to go through them really fast. Okay, 5, 4, 3, 2, 1. Here we go. This one's going up by 2, 1, and 2. These ones are a little trickier because the left side's also going up by different amounts. It's going up by 12. Oh, no, it's going down by 6, by 8, going down by 4. Let's see. Now it's going down by 1. That's going down by 1. Strange. The numbers are changing. It does not seem to be working like the other ones. What's the only one that we have not been able to find by doing that? Well, we have not touched this guy, inverse variation. Remember, inverse variation says if I multiply x times y, I should get the same number every time. So that's really easy to check for. 1 times 12 should be the same as 3 times 4, 4 times 3, and 6 times 2. What do they all make? 12. So this one right here is inverse variation. Okay, the next one. 2, 2, 2. So this guy's going up by 2 is great. This guy's going up by 8, then 16, then 8, and then 16, and then 24, 24. All right, that's not giving me much. Okay, but we can try again. We can go like this and like this. From 8 to 16, it's 8. From 16 to 24, it's 8. Second difference, that's the same as this guy. So it's quadratic. Last one. We got 2, 1, 2. Okay. 18 down to 14, that's down 4. Down 2. And down 4. What type of graph is that? We should say -4, -2, -4. Now here's what I would say. When this changes by a certain amount, that changes by double it, right? If I make a fraction of 2 and 4, that's going to be the same as fraction of -2 and 1. It's going to be the same fraction every time. This actually is just like question 2 here, only instead of changing by the same amount every time, it's changing by different amounts sometimes. But when x changes by a different amount, so does y to match it. So this is still linear. I think that's almost there. Oof, there's a lot to this assignment. Sorry about that. We're almost there. Okay, let's try to finish this thing. Okay, so do these. Where are we at? We're right here. Jay is a biology student. She has a job as a lab assistant for one of her professors. They're doing experiments. She sprays mosquitoes. Her job is to count the number of mosquitoes that die. The table shows how many dead mosquitoes she counted each hour after the insecticide was sprayed. So they're finding out if the insecticide, how long it lasts before it stops killing the mosquitoes. In the first hour, it kills 3,000 mosquitoes. Second hour, 1,500. Third hour, 750. Fourth hour, 375. Okay, there we are. Sketch the graph. Let's do that. I've already numbered it from previous time, so I'm just going to leave it numbered. Notice I counted up by 900, 800, 2,700. I counted up by that because I just wanted to make sure that 3,000 fit. And 3,000 is right here. And then we got to count up to 4. That's easy enough. So 1 goes with 3,000. That's 1, 3,000. Oops, I should make that. All right, 1, 3,000. 2, 1,500. 1,500, 1,500 is right here. Because I'm counting up by 300 each time. 300, 600, 900, 1,200, 1,500, 18. Counting up by 3s with hundreds after them. Okay, for number 3, it's 750. This is 600, that's 900. 750 is exactly halfway between 600 and 900. If I remember correctly, yes, I can do math. That's about here. And 375. 375 is just a little bit more than 300. Around there. Okay, there's my graph. It's going down. It's curving this way. So it looks the most like the inverse one that we had. So maybe it's the inverse one. Well, one thing we could check, notice this is 1, 1, 1, yeah, all that stuff. This goes up by 1s, but what about this guy? Well, he changes by 1,500 first. Goes down by 1,500. Then he goes down by 750 to get 750. And then he goes down by 375 to get 375. Huh. Well, that seems from, hey, those are the same numbers. Guess what happens if I subtract them? I get 750. 750. And 375. That's what I get. I get the same numbers again. So what was that? If I remember correctly, that's the same thing as exponential. It's just that this exponential is getting smaller. It's a decreasing exponential. We call that a negative exponential, or exponential with a negative rate. I know this because oops, the first and second differences are the same for y. For one value, we'll say. Because the other one does not. It's just 1, 1, 1, 1, 1. It's always going up by the same amount. Okay, Jai has also supposed to keep track of the amount of food that they eat. Okay, so they have this much food, and then they have that much food, and then they have that much food. I decided to count up from 20 20.2s. 20.2, 20.4, 20.6, 20.8, 21. 21.2, 21.4, 21.6, 21.8, 22. Just so you know. All right. Why did I do that? Things would fit well. That's half the battle with these types of problems. Notice this only goes from 20 up to 22. So I count by small amounts so that it'll all fit on the graph. Now we count up to 5 on the bottom. We're good. Okay. So 1 goes with 21.5. Let's find where that is. 1's right here. 21.5 is going to be 21.2, 21.4, 21.5. Remember, each line is 0.2. So this is right smack down between 21.4 and 21.6. Now for number 2, that's 21.28. All right. Then we got 3 goes with 21.04. 21.04. That's not even halfway up to 21.2. From there. Okay, notice it's not looking very curved yet. 20.8. 4 goes with 20.8. 20.8. Right? And 5 goes with 20.56. Something like that. Okay, now notice that is not a very curved line. It's not perfectly straight, but I did eye a lot of these. So this is telling me that it might actually be linear. It might be a straight line, which would make sense when you think about it, because if it's linear, that's saying that they eat the same amount every day. That would make sense, wouldn't it? If you're feeding things like this, the pets, the same amount every day, then they're eating the same amount every day. There you go. So compute the first and second differences. What do we notice? Okay. Let's do that. First difference, 1, 1, 1, 1. If I subtract those, I get 0, 0, 0, and that's it, because there's nothing to subtract with. I only subtract the 2 numbers, the one above and the one below, like that. That's why I'm not going up to the top, because there's nothing to subtract this 1 with something above it. Okay, so now we're going to look at these ones. This goes down by, let's see, 52 down to 28. That's going to be 2, 4, 24. It goes down by 0.24. What here? Oh, it goes down by 0.24. And I will just spoil it for you rather than making you work too hard. Down by 0.24, down by 0.24. So it goes down by the same amount every time. If I subtract those, I get zeros again, just like on the other side. The left side and the right side, the first differences are the same on the left and the same on the right. which means if I make a fraction of them, it'll always be the same, which means the slope, the fraction of 0.24 and 1, that is always the same. In other words, they eat 0.24 kilograms of food every day. That's how much food is used up every day. So I can say first differences. First differences are the same. Second differences are 0. Zor, 0. 0. That is, well, that means that the rate is never changing. It's a first degree equation, which means the first ones are the same, which means it's linear. So this is linear. If the first differences are the same, these numbers are the same as each other, on the left side and on the right side they're the same as each other, then it's linear every single time. Oops, I need to put that down lower though. There, perfect. Okay, Chai's professor is doing another experiment. This involves Madagascar hissing cockroaches. Sounds fun. Love myself a hissing cockroach. Ooh, that's cool. We're gonna find out how much oxygen they consume as temperatures increase. So they're turning up the temperature and seeing what happens with oxygen. As the temperature goes up in Celsius, it seems that they use more oxygen. We're going to sketch that graph and see what it looks like. So 10 degrees temperature, 85 microliters per gram per hour. That's kind of fun. Okay, so I already numbered it so that 325 would fit, so I counted by 80s. And then I counted by 10s. I was a little lazy with this one. It's okay. 10, 85, let's find 10, 85 is going to be like right above 80. Okay. 15, 140, 80, 120, 160, so 140 is halfway in between 120 and there, like so. Okay, 20, 220. Oops, that was supposed to be 15. That's my bad. 20, 220, I can move you. Let's see, 16, 200, 240. So 220 is halfway between these guys. Around there. Okay. It's not looking terribly, it looks pretty steep, whatever's going on. 25, 325, 25, 325. 3. This is 260. That is 320. 260 is right here. Something seems off here. I must have made a mistake. Let me double fact check this. Yeah, this 360 is in the wrong spot. Should be 320. Because I'm counting up by 8s, right? 320. And this would be 360. I believe that we're going up by 8, 8, 8. Yeah, and this is actually 400. Miscounted there, and that screwed things up. So now 325 is up here. There. And now we can see the graph starts shallower and gets steeper and steeper as it goes. It seems to be growing what I would call a parabola. How do I know? Because it's getting straighter looking as it goes up this way. But I'm very used to looking at these things. So, all right, it's okay. We can always figure it out using first and second differences. So what are my first differences? This goes up by 5. By 5. Oops, I don't know what I just did there, but I just wanted to type numbers. Let me just type a number. Okay, so that goes up by 5. So that's easy enough. 85 to 140, that's 5 is 90 plus 50, 55. 140 to 220, That's 80. And then from 220 to 325, that's 95. Right? It's 105. It's 105. Too many mistakes. All right. And how far are these guys up? Well, these guys are obviously 0 apart from each other. From 5 to 5 is 0. From 5 to 5 is 0. That's my second difference. From 55 to 85, that's 25 more. And from 80 to 105, that's 25 more. But if the second difference is the same, second difference is the same. Not schema same. Okay, which means the second difference is, oops. For what? For oxygen consumed. Oh, I don't want to turn it on. No. I'm pushing the button too many times. It's made a noise at me. Okay. Quadratic. That means it's quadratic. Quadratic. Right. And that's the end of this. Okay. So here's the things you need to remember. There are 3 types of curves we talked about. Well, 3. There's the inverse variation, which is a curve like this, makes a hyperbola. That means x times y makes the same number every time. There is the parabolic curve, or the quadratic curve. Or I should say this is parabolic. That's the name of that type of curve. Parabola. That's one that we definitely deal with in high school a lot. And then there's the, by the way, with parabolas, the second difference is always the same. And finally, we have our exponential curve. That means that it goes up by the same factor every time instead of by the same amount. Instead of adding, we're multiplying every time. And it starts out really, really slow and grows faster and faster. So if it kept going, it would look like this. It would look really steep as you go. All right. And we found out ways to find each one. If something is linear, then the first differences will always be the same. If something is quadratic, then the second difference will always be the same. What I mean by always the same is all of the numbers are the same as each other. However, if you do first differences, second differences, third, if I keep doing that for exponential functions, it always makes the same numbers as they started out. So they never change. Like the literal numbers, the differences never change. They're different from each other though, like going up and down the list. And finally, inverse variation is just weird, but the way to check is to see if these numbers multiply the same as those and those. 12 times 1, 3 times 4, 4 times 3, 6 times 2, they always make the same number. And that's how you can tell. And that's my video. Have a wonderful, wonderful day. Last one of the semester.